All right, everybody, welcome to the video for lesson number 8 on applications of geometric series. So in today's lesson, we're going to use the new formula that we learned in lesson 7 for a series of a geometric sequence. And we're going to apply it in a couple of different ways. You're definitely going to want your calculator for today's lesson, so go ahead and grab that. And I'd like you to try the opening exercise, see what you get for your answer. All right, so welcome back to the video here. So hopefully you tried this. This is a throwback question to just our exponential growth problems that we did. This was a monthly deposit, so or a monthly interest rate. So we used 12 for n. 0.036 winds up being our interest rate, so we use that, and we can go from there. Now, in looking at all of this, one of the things that we remember, hopefully, from all the work that we did with exponents is we can clean this value up. So if I type just that value in my calculator, 1 plus 0.036 divided by 12, I get 1.003. And that represents my common ratio, or my multiplier, to get from one year to the next year if we needed to. Now, we're going to use this idea in question 1. So question 1 says a $100 deposit is made at the end of every month for 12 months. That's very different than what the opening exercise question is saying. I'm not saying that you have $1,200 and you're earning interest over the course of the year. I'm saying every month you're adding a new value to this. Now, the interest rate is the same. It's 0.36 compounded monthly. So this 0.36 compounded monthly, that's going to be this value. So every month, I'm going to multiply that to the previous month's ending balance. So after month 1, I have $100. There's month 1. We'll even call that, we won't use A. We'll say month 1, M1. After month 2, I'm going to take that $100, multiply it by 1.003, and add another $100. After month 3, I'm going to take this value, 100 times 1.003, raise it to the second power, add 100 times 1.003, and add another $100. So I'm taking the previous month's value, multiplying it by another 1.03. I'm taking the new month's value, multiplying it by 1.03, and adding another $100. If I keep doing this for 12 months, eventually I'm going to get this long sequence of numbers that follows a geometric pattern. Notice each time I go up another month, I would add another term. So if I wanted to find the value for month 4, it would be 100 times 1.03 to the third, plus 100 times 1.03 to the second, to the first, and then add 100. So this in itself is a geometric sequence. So if I wanted to find the value in month 12, it would be 100 times 1.003 to the 11th power. That would be the last term that we'd have there, plus a bunch of stuff. I'd have a plus 100, 1.03, plus 100. So we can see this pattern, and it looks very similar to some of the things that we did in other problems earlier in this chapter, noticing its geometric in nature. Now, from this pattern, if I can figure out what this value is, I know how much money I would have after the 12th month. Well, since it's geometric, I can just use this new sum formula. So the series formula was a sub 1 minus a sub 1 times the rate to the nth power, all over 1 minus the rate. That's something we learned in the previous lesson, lesson 7. So now I'm going to just apply that formula to find the value in month 12. So the initial value was 100. The common ratio, each time I go up a month, I'm multiplying by another 1.003. I need the value after 12 months. And then 1 minus 1.003. Now I just have to type that into my calculator. So when typing that into calculator, if you have the alpha y equals fraction button, use it, right? It's your friend. So if I type that into my calculator, 100 minus 100 times 1.003 to the 12th power, all divided by 1 minus 1.003. I get $1,219.99, so we have to round that. So we have $1,220 if you round that to the nearest cent. All right, let's take a look at another question, very similar. So it says, when Julie was born, her parents invested $2,500 in an account that compounded an annual rate of 2%. So an annual rate of 2%, that's going to be 1.02. So every year, we're going to multiply the previous year's value by 1.02. It then says, on her birthday every year, the parents invest another $2,500 into this account. Very nice parents. So after she graduates college, she can access the money in this account. So to write a recursive formula, recursive means we need two things. We need the initial value, so the first year is $2,500, and we need a rule. To find the next year's value, we're going to take the previous year's value, multiply it by 1.02, and add another $2,500. So that's my rule. Now this sequence, if we were to write the sequence out, is going to look very similar to the one we just did up here with the $100 a month, right? The first year, year one, is going to be $2,500. Year two is going to be $2,500 plus $2,500 times 1.02. Year three is going to be $2,500 plus $2,500 times 1.02 plus another $2,500 times 1.02 to the second. And that sequence is going to go on and on and on forever. So if I wanted to write an expression in terms of n for the number of years, we would say S sub n is equal to the initial amount of money minus the initial amount of money times the common ratio, 1.02, to some number of years, n, all divided by 1 minus 1.02. That formula will determine how much money Julie has in her account after any number of years. So you can figure out how much money she has after 2 years or 5 years or 6 years just by plugging in the value of n for the number of years. So it says Julie will graduate college soon after her 22nd birthday. Determine the amount of money that's in this account at her 22nd birthday. So this is just asking us to find, well, what's S sub 22? So we're just going to plug into the formula we created above. And Julie is going to be a very rich lady. Her parents did a nice job here of saving her money. If you type this into your calculator, you get $68,000, $247.46. Now, in class, I would even ask a question here. I'd say, how much money did the account earn just in interest? So this question's not on the notes packet, but it's something to talk about because it's interesting to see how much money you're saving compared to if you were to just put this in a general shoebox in your bedroom and just keep the money, right? How much money is the bank actually giving you in this case? So the parents deposited $2,500 for 22 years. So if I do 2,500 times 22 years, that's $55,000. Very nice gift that the parents gave her, but because the parents were smart enough to put it in an account that earned 2% interest per year, notice how much more money they earned because of that. So for you to subtract those two numbers, you wind up making about $13,000 extra just by putting it into this account instead of just saving it and hiding in your house somewhere or something like that. This is how retirements work. This is how IRAs work, and a lot of other things that eventually you'll all start thinking about or talking about at 15, 16 years old. You're not really thinking too much about this, but when you are starting to invest money when you're in college or right after college, it's important to understand where the money's coming from, right? And this is a lot of money coming directly from the bank just by giving them the money. So on the next page, we're giving you a formula here that sometimes comes up on the Regents exam. It's a variation of the sum formula. All they did was they did some factoring and some combining of like terms and moving terms around. It's called the Annuity Formula. It's basically the same exact thing as the sum formula. We're just using different pieces. So R I, all these things represent things. So R represents the recurring payment. I, in this case, is just the interest, right? So this is not 1 plus the R, it's actually the interest rate. So if it says 3% interest, you're going to put 0.03 there. And you can figure out your amount of money in this annuity after a certain number of years by using this new payment. But again, just to be clear, it's the same exact thing as this formula. So unless they specifically ask you to use this formula, you can always use the regular series formula. If you're really interested where this annuity formula came from, just Google it. Right? Google how the series formula becomes the annuities formula. You can see all the algebra that goes along with combining and making that. But I'm going to still primarily just use this one because we're just getting used to it after one lesson. I want to make sure that we're okay using this formula. So let's take a look at another problem. So it says find the interest earned and the future value of an annuity with monthly payments of $200 for 2 years, an account that pays 6% interest compounded monthly. So compounded monthly, 6% interest, that's going to be 1 plus 0.06 over 12. That's going to be the number that's in your parenthesis. That's what I'm multiplying, right, every single time I get from 1 year to the next. So if I clean that number up a little bit, 1 plus 0.06 divided by 12, I get a value here of 1.005. So if we look here, it says we're taking a monthly payment of $200. So after month 1, I have $200. After month 2, I'd be at $200 plus $200 times this rate of 1.005. After month 3, I'd have 200 plus 200 times 1.005, and then another 200 times 1.005 squared, because every month we're adding that interest to the previous month's value. So you can see that as we keep going here, each month it's generating this geometric pattern. Now it wants us to do this for 2 years. 2 years is going to be 24 months. So I want to find the series value at 24 months. So instead of me figuring out what the M sub 24 value is and adding it all up, I could just use this formula. So the first payment was $200. That's the initial amount. The rate is 1.005. Raise that to 24th power. And I'll do 1 minus 1.005. Well, if I do that, I then can type it in the calculator and see what you get. So go ahead, do it along with me. Make sure that you're getting the same value. All right, so if you did it right, you got $5,086.39. Could you have done this same problem and got the same answer using this crazy version of the formula up here, this A of F formula? Absolutely. But I don't want to teach you a new formula, right? We'll eventually use it later on in the lesson. But for right now, let's just keep practicing this sum formula. Okay, actually, we might use it in the next lesson. I'm not sure yet. We'll see. So let's go on to the next problem. Next problem sounds very similar. So it says how much money would be needed to invest every month into an account for an annual interest rate of 12% compounded monthly. So 12% compounded monthly, that's going to be 1 plus 0.12 divided by 12. If I plug that into my calculator, just to make it easy for us, I get 1.01. Now, the difference here is I don't know what the first value is. That first monthly payment is the monthly payment. So if I figure out what the first value is, I'll know how much every month is being invested here. But I do, however, know the sum. I know the sum of the series after 18 months. So I know S sub 18. So I could say 3,000 is equal to, I don't know the first value, I'll just make it A instead of A sub 1, times the rate to the 18th power, all divided by 1 minus this rate. Now we just have to do some algebra, right? So I'm going to clean up this denominator, 1 minus 1.01, that just becomes negative 0.01. And if I multiply both sides by negative 0.01, this cancels, and I'm left with negative 30 is equal to A minus A times 1.01 to the 18th power. Now, in the previous lesson, we would have evaluated 1.01 to the 18th power and combined like terms. You can do that here, but you're going to come up with a messy decimal. So I'd rather not do that. I'm going to show you an alternate way of doing it. So instead of that, I can just factor out A. If I factor out A, I'm left with this. So this value, 1 minus 1.01 to the 18th power, it is a number, right? It's going to be, negative 0.19614, something like that. It doesn't change to a nice fraction or anything like that. So I don't want to use that decimal. I don't want to round it. So I'm going to divide both sides by this parenthesis. Because I have a calculator, I can do this, right? I don't have to worry about getting crazy with the rounding. And if I just type that into my calculator here, I get a value. So if I type that into my calculator, negative 30 divided by 1 minus 1.01 to the 18th power, I wind up getting $152.95. So to create a monthly payment in 18 months to make $3,000 with this compounding interest, I would have to put in $152.95. So we can use this and kind of think of a savings plan. So let's use Mr. Hines as an example. He's young, so he's probably starting to think about how he could retire. So it says Mr. Hines invests $100 a month in a savings plan. So when he retires 40 years from now, he has all this money that he can use. It says it earns 6% compounded monthly. How much money will he have when he retires? So 40 years is a value of 480 payments. So I want to find the value of S sub 480. I know the initial amount of money, it's 100. I know the rate 6% compounded monthly, I would say 1 plus 0.06 over 12. If I type that in my calculator, that should come out relatively nice. I get 1.005. And that's the 480th power. And then 1 minus 1.005. So this is going to find the value of the 480th month, right? It's going to add all months up to 480. So if we type that into the calculator, we see that after 40 years of investing $100 a month, Mr. Hines is going to have $199,149.07. Now, unfortunately, that's not a lot of money. You might think that's a lot of money, but to retire on, that's not enough money. Mr. Hines has bigger aspirations than that, right? He wants more money. So after doing this little bit of math, Mr. Hines said, well, I don't want to retire with $200,000. I want to have $1 million. I want to be a millionaire, right? We want Mr. Hines to be a millionaire. So let's figure out how much money Mr. Hines would have to put into the same account to be a millionaire. So I want the ending sum to be $1 million. I don't know the monthly payment, so I don't know the first month's payment, but I do know the rate, or the common ratio. I know how many payments I'm going to have. And I should be able to solve for A. So this is a good opportunity for you to pause the video, take what I did here up top in exercise 4, and try and figure out how much money a month Mr. Hines has to put in to make $1 million. I want Mr. Hines to be a millionaire. All right, so let's take you through step by step what I did here. So the first thing I did was I cleaned up the denominator. If I do 1 minus 1.005, I get negative 0.005. I then multiplied both sides by negative 0.005 so that these would cancel. That left me with negative 5,000. I then noticed that both terms here have A in it, so I factored out A. And then I divided away this crazy parenthesis of 1 minus 1.005 to the 480th power. This then gets plugged into the calculator, and I get $502.14. So if Mr. Hines wants to end his career in 40 years and be a millionaire, he'd have to put $500 a month into this account that gives us this interest of 6% compounded monthly. Again, if you notice, we're really just using the same formula we did in lesson 7. We're just doing it kind of in a different way. That's all we're doing here. Okay. Exercise 6 is busy work. We're just going to skip it. It's basically the same exact thing again. All right. So here's a good opportunity for you to pause the video, try the homework on your own, and then come back to the video and see how you do. All right, so welcome back. Hopefully you tried these questions on your own. So it says to find the sum of this series. It's geometric. I know it's geometric. It has a common multiplier. I have the first term, the second term, and I notice each term has an exponent that's one less than the term number. So this would be the 60th term. So if I wanted to find the sum of these 60 terms, I would take the first term, subtract the first term, multiply by the common ratio to the 60th power, all divided by 1 minus 1.01. Use that fraction button in your calculator. And we get 73502. I'm assuming this is money, 0.71. All right, let's take a look at the next one. The next one's written in summation notation. So if you have the new calculator, you literally could just type this in the calculator as is and find the sum. If you don't, or you just want to practice this new formula, what we're doing is we're finding the sum of the first 48 terms. The first term is 15,000. The common ratio is whatever this number is. So if I do 1 plus 0.04 divided by 12, I get 1.003 repeating. We're going to do that to the 48th power, divided by 1.1003 repeating. Now to do that with the repeating decimal, you probably want to use a fraction. So 1.003 repeating is actually 301 over 300. So when I type that into my calculator, I don't want to use the decimal because that's rounded. So I'm going to actually use a fraction here. It looks messy, but you're just typing it into the calculator, so it really doesn't matter. So if you type this in, use that fraction button to make your nice fraction. 15,000 minus 15,000 times 301 over 300 to the 48th power, all divided by 1 minus 301 over 300. Again, typing this in with me is important so you can see that you're getting the same answers as me. Since it's all kind of looking like money, I'm just rounding everything to the nearest hundredth. It would tell you specifically what to round to unless it was money. All right, let's look at the next one. So it gives us this alternating sequence. So it goes from positive to negative. I know the first term is 1. To get from one term to the next, it looks like I'm multiplying by a common ratio of negative 1/2. And I have to figure out how many terms there are in this sequence. So my explicit formula for this sequence would be 1 times negative 1/2 to the n minus 1. So if I do 1 times negative 1/2 to the, and at this point I'm really just guessing. If I do 8 minus 1, and then change that to a fraction, I get negative 1 over 128. So it's not the 8th term, it's bigger than that. So let's try the 9th term. Change it to a fraction. That's 1 over 256. So that must mean it's the 10th term, but let's try it. All right, so if I plug in 10 minus 1 as the exponent, this becomes the 10th term. And again, there's nothing tricky to that. I am literally just typing in numbers for n until I get negative 1 over 512. So what this question is asking us to do is find the sum of these 10 terms. The first term is 1. Common ratio is negative 1/2. And I'm just asking you to plug that into the calculator. So try it and see what you get, right? So make your fraction 1 minus 1 times negative 1/2 to the 10th power divided by 1 minus negative 1/2. And we wind up getting a decimal which changes to a fraction of 341 over 512. The decimal is 0.66601. I don't like to write 0.66 down. That's just not right. So let's take a look at a multiple choice question. So it says Natalie's working and she's saving $1,200 every year. The account grows annually at a rate of 0.43 compounded annual, right? So that's going to be a rate or a common ratio of 1.043. Which expression is going to be her account after 20 years? So it's just the series formula, right? So I'm going to do the 1,200 minus 1,200 times the rate to the 20th power, all divided by 1 minus that rate. So it can't be choice 2 and it can't be choice 4. They don't even have a division sign. Now, the reason why 1 is not good, this is not the right common ratio. That's the interest rate, but it's not what we would multiply from one year to the next. The answer is choice 3. Now, you might be saying, well, choice 3 doesn't have 1 minus that number, but if I do 1 minus 1.043, guess what I get? I get negative 0.043. That's the number right here. That was actually a nice multiple choice question I put on a Regents exam a few years ago. All right, let's keep going. So it says how much money should be invested every month with an 8% interest rate compounded monthly in order to save $10,000 in 15 months. Notice they gave us this annuities formula. I'm not going to use it today. All right, I'm going to use that more in lesson 9. I'm going to still use this sum formula. So the first thing I have to do is figure out, well, what's 1 plus 0.08 divided by 12, because it's a monthly rate. So if I do 1 plus 0.08 divided by 12, I get this decimal that's a repeating decimal, which becomes 151 over 150. That's the number I want to use wherever I see rate. So if I want to find the sum of 15 months, I'm going to take the initial amount of money, 10,000, minus 10,000, multiply it by the common ratio, raise it to the 15th power, and then do 1 minus the common ratio. I know you don't like fractions, but the decimal is a repeating decimal, so we can't round it. So let's type that in and see what we get. So if I do 10,000 minus 10,000, make sure you have the right number of zeros and all those big numbers, right? Times the common ratio to the 15th power, 1 minus the common ratio. And we get its money. So we'll say $157,206.33. Number 5 talks about the Smiths setting up an education account for their son. They deposit $5,000 and it pays 2.7 compounded annually. So compounded annually tells us that the common ratio is going to be 1.027. No need to divide by 12 or anything crazy like that because it's annual. It then says, beginning on his first birthday, to deposit initial $300 in the account for each one of his birthdays. Write a recursive rule that represents the amount of money in the account and years after their son was born. So let's think about this for a minute. So the initial deposit was $5,000, and then every year after that, they add another $300. So year 1, they have $5,000. Year 2, they're going to put $300 in, and they're going to add that to the previous year's value, 5,000 times 1.027. Then in the next year, right, they're going to take whatever this value was, they're going to add another $300. Then they're going to add the previous year's $300 times 1.027. And that original $5,000, well, that's going to get 2 years of interest, so it would be that value squared. So if I want to find year 3, be another $300. The previous year's value, right, that 300 gets another 1.027. The second year's value gets another 1.027, so that would be squared. And the original $5,000, well, that's going to be 1.027 to the 3rd power. So to write a recursive rule here, right, we're starting with year one, $5,000. The next term is going to be whatever the previous year's term is times 1.027 plus an initial $300. Now, when you're looking at it, this recursive formula looks a lot different than what I wrote out here, but it's saying the same thing. So when I found year two, I added $300. That's this 300. And then whatever the previous year was, I'll circle that in a different color here, right? This was the previous year's value. I multiplied each one of those pieces by another 1.027. That's how I'm getting from one year to the next. So there's your recursive rule for this formula. Now, you might be looking at this and saying it's not geometric, and it's because it's not. Because of the initial investment of $5,000 being different than the yearly investment of $300, I can't write a geometric rule for this, so the only rule I can actually come up with would be a recursive rule. So if I wanted to figure out how much money he had on his, say, 18th birthday, I'd have to actually find the value of all 17 years before that and add it all up. That would be the only way of doing number 5. They wouldn't ask you to do that. I wouldn't ask you to do that, right? My interest here is just that you see how the pattern is coming to come to fruition here. Okay, hopefully this video helped. Lesson 9 will work more with that annuities formula, and we'll eventually be buying a house and a car, right? Our wonderful project that we did in the last chapter, we'll kind of revisit it using sequences now, and we'll go with that in the next lesson. Hopefully I see you soon.